Quantum Pune. So before hand over the session to Mr. Amit Saha, I would like to briefly introduce him. So Mr. Amit Saha is currently working as a quantum expert and consultant at Atos Quantum in Pune. So he is also pursuing his PhD from University of Calcutta in the domain of quantum computing since 2016. He was a senior research fellow of CSIR from 2017 to 2019. His current research interests include quantum computing, quantum algorithm, quantum circuit synthesis, multi-valued quantum computing, quantum image processing, and he is author of several papers on these topics. So I welcome you, sir, Mr. Amit Saha. Please, sir.
Yeah. Thank you for
Yes,
your
please.
kind introduction. Am I audible?
Yes, sir.
Thank you.
Yes.
So, okay. So let me stop my video first because yeah. Am I audible?
Yes.
Yes.
Yes, audible.
Okay. So I'm facing some network issue right now because this live is. So I'm from North Bengal. So kindly some bad weather is going on here. So that's why I'm stopping my video, and I'll just explain whatever I have today for you. So let me first share my screen. Just a minute. So are my slides visible?
Yes, sir.
Okay.
Yes, it is visible.
Okay. That's good. Okay. So I'd like to I'd like to have more interactive session. I believe you all are going to be more interactive with me during my presentation. And if anyone has any question regarding my slides, you can ask me there. You can stop me there. So my today's topic is a demonstration of an algorithm level implementation on quantum computers. So yesterday I followed 3 lectures that are given by my supervisors, Dr. Shushmita Shulkole, Shudhendu Bikash Mandal, and the Dr. Amlan Chakraborty. And today also I got some time to follow the last lecture, and I found that you all are already know what is actually quantum computing, what is qubits, what is superposition, what is entanglement, what are the gates. So I'm not going to discuss those things again in my slides, because my today's talk is like a optimization problem where the constraint is time, because I have given 45 minutes and I have to finish my demonstration in this 45 minutes. So let me introduce myself. My name is Amit Shah, and currently I'm working at Atos. And as you can see that Atos QLM. So QLM stands for quantum learning machine, and it's a product from Atos. And it's so back in 2017, Atos came up with a powerful quantum simulator that is the world's largest qubit simulator right now, which have 41 qubits. And I'm going to demonstrate my algorithm on this Atos QLM platform. And as last speaker mentioned in the last slide, that Amazon Bracket has come up with a platform, and it's giving a chance to program to the known quantum processing unit. And so my organization ATOS has already come up with this idea in 2017. So we have a quantum simulator, and it has a quantum platform from where you can write your own quantum programming, and with a single line of code you can fetch your total quantum program into the known quantum processing unit like IBM or the Rigetti or the Microsoft has. So let me discuss about the quantum learning machine first. So I'll take only one slide to discuss about quantum learning machine. So it's a quantum simulator that I have already told you, and it's come up with a quantum programming platform like you have already seen in last 2 or 3 days in regards to Qiskit or the IBM Q has. All right, so it's nothing but a Python quantum platform Atos QLM has. So you can see that so generate quantum algorithms without quantum hardware constraints. What does it mean? So yesterday Omlan sir has already told you that that whenever you have to implement your quantum algorithm or the quantum circuit to the quantum hardware, you need to know the topology of the quantum hardware. Is qubits are qubits 2 qubits are neighbor or not? You have to have the knowledge of this kind of topology of quantum hardware. But whenever you are working on Atos QLM, you don't need to bother about the quantum hardware constraints. You need to write only the quantum program for your specific problem, and you can just implement your algorithm into any of the known quantum hardware. So in Atos QLM platform, you can describe your quantum circuit. This is the second point of the QLM slide. You can simulate your overall qubits or the overall quantum circuit in our simulator. And so already I have told that if you can write one line of code, you can implement your algorithm in the known quantum hardware. So what does it mean? So there are two or three advantages I can give right now. So whenever we are running a program in IBM's machine or the just previous speaker told you that DUF has a platform. So you are running your algorithm into the cloud platform. So this is not very secure indeed, isn't it? Because you don't know that where is your quantum programming actually implementing. So it's not very secure at all. So we are actually providing a quantum simulator as a classical hardware, and you can run your own program very securely. And also we are giving a quantum computing platform where you can write your algorithm, and you can implement your algorithm in any of the quantum hardware. So you don't need to learn all possible quantum languages, because DOF has their own language, IBM has their own language, Rigetti has their own language, Microsoft has their own language. So you don't need to bother about the different type of languages. You just need to learn our Atos quantum learning machines language, and you can implement your algorithm in all possible quantum hardware. So this is the introduction I want to give you about our Atos quantum learning machine. Now I would like to more I would like to discuss more about the programming part of it. So so you can see that our language is known as AICTE. So AICTE is nothing but the Atos quantum assembly language. So QASM, it's already been told by many speakers, but so it's a special version for Atos, and you can see that these are the known gates to you, and we can describe them with the AICTE keyword like this. For Hadamard, like H, for Pauli X, X, and for like X rotation, Y rotation, you can describe them like this. So these are the 1 qubit gates that I have shown in this slide. Next, some matrix representation of the 1 qubit gates. I believe all are covered by the previous speakers, so I just skip this slide. These are some so these are some multi qubit gates like control not swap, control Z Toffoli. So these are the important gates to build up our own quantum algorithm, and you have to. I believe you have already understood all the quantum gates very well. So I'm also skipping this slide. So like yesterday I saw that Shudinduda has given you a good hands-on on Qiskit. So so our platform is not far behind from IBM's Qiskit, I must say. We also need to start with declaring the quantum program like Qiskit does. So as you can see that we have to first import the program Hadamard or CNOT. As I'm going to talk about Hadamard as CNOT later, so I'm already importing them from cat.lang.acasm module, and I have declared the qprobe as our quantum program. All right. Then we have to declare the qubits. So as I am going to show you an example of 2 qubits entanglement. So I have taken 2 qubit. As you can see that qubits equals to qprobe dot alloc 2. What does it mean? It can allocate 2 qubit into my program. So you can see that 2 qubits, q0 and q1. Next is I have applied H gate on the first qubit and C0 gate between so C0 gate in q0 as control and q1 as target. So it's nothing but 2 qubits entanglement circuit, or as we all know, in last 2-3 days many people have already discussed this thing. So now, so from where we from importing these program program Hadamard and C0, we have allocated the qubits first, then we have applied the gates. Now we need to convert this program into this circuit. So how we'll do? So we need to convert by this operation to circuit. So now it's become a circuit. So next, what we have to do? Next, we have to simulate that circuit to get the actual result out of it, isn't it? So for that, we need to declare the simulator. So so I have taken the most simplest simulator, that is linear algebra simulator from our QLM machine, and I have declared and I have created a quantum processor unit for implementing or for simulating my my circuit. So it can be done as like my lineal QPU that is declared by me, and I'm just calling the lineal function that QPU actually, that actual simulator. Next, what I have to do. Next, I have to create a job for that specific circuit that I have already declared. So I have defined the job and create a job. So circuit now becomes a job, like Shudin Duda has discussed yesterday's session. So now my circuit has become a job. So next part is I have to submit this job to the simulator to get the result out of it. So what I have done, so I'm taking the results out of it, and I have submit the job to my my linear QQ that I have defined earlier. So from this point, what we want to show as result, first we want to see the circuit, output circuit. Next we want to see the measurement result, isn't it? So for visualizing the circuit, we need a magic function in QLM, and if you write percentage cat display circuit, it will directly show the outcome of the circuit. So it's nothing but the entangled 2 qubits entanglement circuit. And if you want to know the outcome of this circuit, so you have to write a 2-line code from which you can get the result. You can get the result of this particular circuit. So as you know that for 2 qubits entanglement state, it's nothing but 1/√2 0 0 1 plus 1 1. So it's showing the amplitude of getting 0 0, that is 0.70, that is nothing but 1/√2, and 1 1 with 1/√2. So if there is any confusion, that confusion will be cleared in the next slide. So as you can see that this is a circuit I have. So I have declared Hadamard here on the first qubit, and next is a C0 gate. So so this circuit can be visualized in this way also. So whenever we don't have any gate in a timestamp, we can declare them as identity. So in timestamp 1, so I can say them as G1, which has Hadamard on first qubit and identity on the second qubit, and in G2 timestamp there is a control node. So mathematical, if you do the mathematical analysis, so it starts with 0 0 qubit. So you can see that it's 0 0, and next is we have applied X tensor I. So I just saw in the previous so I saw in the previous discussion that the speaker has already mentioned the tensor network, or the tensor product also. So it's a tensor product. So it's a tensor product between H and I in the timestamp 1. So if you have the 0 0 initial state, then after applying H tensor I, you will have 0 0 plus 1 0 over √2. So is that clear to all of you?
I think participants can raise their hand, so Prem can unmute them.
So
any question, you can raise your hand. Partho.
Yes, sir. Partho sir has some question.
Yes,
Partho sir,
yes.
please.
Actually, this is not actually clear because I am very new to this field.
Okay.
And how this come in result that this H parameter, that is H, H factor is changing this Q0 to Q00.
Yeah,
Could
yeah,
you
yeah.
please explain?
Yeah. I'll explain. So So can I? Yeah, I can write from here, isn't it? So which one is pen? This one, isn't it? So I can write by this one. I'm not very much familiar with Zoom, so I can I write with this one, or
Sir, you can annotate there. There will be option of pen like thing to annote.
which one?
I
At
have
the
one
top
question.
where is share screen options are available, you can
Okay.
just move the cursor mouse to the top of the section, and you can find there annote.
Yeah, I got annotate option, but which option I have to select? I don't understand.
Yes, sir, it is coming. Pen is coming, sir. Yes,
Pen is coming. Okay. Okay.
yes.
So yeah, pen is coming. So initially we have 0, 0, isn't it? So initially we have 0 over here, 0 over here. Is this clear to all of you? Initially we have 0 quantum state on qubit 0 and 0 quantum state on qubit 1. So now if we apply Hadamard on first qubit, then it will become 0 plus 1 root over 2 tensor of 0, because I'm doing nothing with the second qubit. So it will become 0 plus 1 by root over of 2. So it is nothing but, so let me, if I apply Hadamard over here, it is nothing but a superposed of 0 and 1. Okay.
Okay.
So, and in case of second qubit, I am applying the identity, so it will remain the same. So if we do the, so now if we, so initially we have 0, 0, now we have applied H tensor I. What does it mean? 1 over root 2 over 0 plus 1 tensor of 0, 0. Okay. So if we multiply this, so this is nothing but this one. Now it is clear.
Yes.
Okay, thank you. So now if I apply a C0 on this, so we know that C0 is a quantum gate which is completely based on the control operation. If the control operation is 0, then it will not change anything on the target. If it is 1, it is going to change the target. So you can see that the control is on first qubit. So control is on first qubit. So if it is 0, the second qubit remains same, like 0, 0. If as it is 1, second qubit becomes 1. So now it becomes an entanglement state. So it is I believe the mathematical formulation of entanglement is clear to all of you now. Am I right?
Thank you. I got it. Thank you.
Okay. So
I have
yes.
one question.
Yes.
The product which you have shown here, the tensor product.
Yeah.
How it differs from the normal dot product? Because
I'm coming on the next slide.
Let me finish, then you will respond.
Yeah.
I said that what you have shown here, this is nothing but a dot product, but you said that it is a tensor product. So that I want to understand why this is tensor, not a dot.
Yeah. I'm coming on the next slide. Can I proceed?
Yeah, go ahead.
Yeah. Thank
Yes,
you.
yes, you can.
Yeah. So I have. So it's not okay. So I have. All right. I have to delete this things, isn't it?
I think there is a eraser.
Yeah. I got it. Yeah. Thank you. Okay. Yes. Uh, so I have discussed the entanglement property of two qubits in more mathematical in the previous slides. Now I want to discuss more about this property in case of simulation. I mean, what actually simulator does when it is getting the circuit. So as you can see that in timestamp 1, G1 is nothing but H tensor I. And H is nothing but the 1 over root 2, 1 over root 2, 1 over root 2, minus 1 over root 2, and tensor of identity matrix, which is 1, 0, 0, 1, isn't it? So coming to the question from audience that what is the difference between normal product and the tensor product. So normal product gives us, like, if we do the normal product of this or the matrix multiplication, we have to do the matrix multiplication, we can have only 2 cross 2 matrix as an output. But if we do the tensor product over here, so we will have a 4 cross 4 matrix as quantum state, because we are dealing with 2 qubits, so we will require 4 cross 4 matrix to perform the quantum simulation of this particular circuit. So we are actually dealing with the tensor product for the quantum circuit. So you can see that how it's happening. So a tensor product is nothing but this with multiplication with this one, this with this one, this with this one, and this with this one. So ultimately it yields this matrix from G1. So now our G1 is nothing but this matrix. And as we know that G2 is nothing but a C0 operation. C0 operation is nothing but like if we have 0, 0 over here, so there will be no change. For 0, 1, there will be no change. For 1, 0, we have will have 1, 1. So this 2 row has been interchanged in case of C0, and for 1, 1 it will be 1, 0. So is this clear to everyone? This gate, C0 gate?
One more questions from the participants, actually from Tanoy Chattopadhyay. Sir,
Yeah.
would you please tell me why tensor product comes here? I see that these are different register line.
Yeah, that's why if you are dealing with 2 different quantum register line, you must have to do the tensor of it, because then only you will have the extra dimension, isn't it? When you are performing the when you are performing the row operation of the gates, then you will have to do the multiplication. When you are doing when you are doing tensor product between 2 quantum gates, then you are dealing with the 2 quantum register. Did I make any sense? Because you have to be clear on this point.
Is it possible to change the dimension of the matrix and then we have the normal product? I think that will
Yeah, that's why we need to change the dimension of the matrix. That's why we are doing the tensor product.
Use a tensor. We can just apply the normal dot product.
How does it possible?
No, I'm asking, is it possible?
No, sir. This is not possible. That's why it's a fundamental property. I can't do it. It's not discovered by me. It's a fundamental property that whenever you are dealing with two or more different qubits and you have a different gates on a single timestamp, you have to do the tensor product of those quantum gates, and then you have to multiply all the quantum gates. So I'll come in the next slide. So now we have G1 as this matrix, and G2, as we know that this is C0. So I think this is clear to all of you, isn't it? Why this is interchanged? Okay, let me write this again. Just a minute. Yes. So in case of C0, what is happening? If we have 0 0, it will 0 0. If we have 0 1, it will give 0 1. If we have 1 0, it will give 1 1. And if we have 1 1, it will give 1 0. So in this matrix, you can see that it is actually defined by 0 0. It is 0 1 1 0 1 1. So this first row is 0 0. This second row is 0 1. This one is 1 0. This one. So for 0 0, it remains same because there is no change. For 0 1, it remains same. So as if you have the identity matrix there. So let me write. So if you have 1 0, so now it becomes 1 1 because this has changed to this position, and for 1 1 it becomes 1 0. I think now it is absolutely clear to all of you what is happening in C0 matrix.
Yeah, it's clear. Thank you.
Yeah.
Okay, Mr. Vikas Nignath, you want to ask something? You have raised your hand. Hello?
No.
Okay. One more question from Dr. Lata.
Yes.
In case of tensor product of 3 qubits, what would be the dimension of resultant matrix?
Yeah. So you can see that. Let me try again. Yes. So your question is you have 3 number of qubits. So if so for like I have 0 0 or 0 or maybe 1 here. So these are nothing but or suppose you have just 1 2 3. Suppose you have a single qubit gate over here. You have a single qubit gate over here. So for this gate, you have 2 cross 2 matrix. Suppose A, B, C, D. For this gate, you have 2 cross like A1, B1, C1, and D1. And for this one, like A2, B2, C2, D2. Then if you tensor this 3, then you will have 8 cross 8 matrix over here. So it becomes, so if you have 2 number of qubits, then you'll have 2 square cross 2 square matrix. If you have 3 number of qubits, you will have 2 cube into 2 cube. That means if you have n number of matrix, you will have 2 to the power n cross 2 to the power n number of matrix. I think it's clear to you now. Is this clear to you, ma'am?
Yes.
Yes, yes.
Okay,
We have
thank you.
written, understood.
Then, yes.
So where you were actually, so we mathematically proved that how entanglement is happening. Now we are actually showing how simulator giving us the output of that circuit. So first of all, we did the tensor product of this two, and we have G1 and we have G2. Now we have to multiply these two matrix in such a way, like if we, yes, so we have to multiply our two G2 and G1 in right to left order. That means you have to first put this matrix G2 first, then followed by G1. So if you have like 10,000 number of gates in your hand, you have to start from the like 1,000 number of timestamp gate, then 999 and like this. So you now you have a G2 into G1 and you have a G. So this is become, so this overall becomes G, and this is nothing but this matrix. So is this our output? No, this is not our output. This is not our output because we haven't initialized our qubit yet. So now we have to initialize our qubit as 00, and we know that 00 is nothing but 1000, as Shudindu yesterday mentioned, that like 0 is 10, 1 is 01. So similarly 00 is 1000, 01 like 01, 00 and goes on like this. So 00 is nothing but 1000. Now we have to multiply this thing with this part, because we have G over here, and now we have the initialization Q0 and Q1 as 00, and we need to multiply this G, because it will go right to left. So G will come first, followed by 00. So if we multiply this two matrix, we'll have the final outcome, which is the first column of the matrix, isn't it? So this, what does it mean by this column matrix? This means that 1 by root 2 with 00 gate state, and 1 by root 2 with 11 gate state, and 0 with 01 and 0 with 10. That means as we know that our output is nothing but 1 over root 2 00 and 1 over root 2 11. So simulator is simulating our circuit in this simpler way. So this is the simplest way to simulate any quantum circuit that I have shown right now. There are other advanced simulation method like matrix product state or the BDD based. So I'm not going to talk much about them, because I'd like to as much as possible simple this presentation. So I believe everyone has understood that. Yes, yes.
I have a simple question, that
yeah,
why are we multiplying actually by phase? I mean G2 into G1 or G3 into G2 to get G1, then G2 into G1 to get G.
Yeah.
So what is actually I mean, what is actually implementing? It is registered or something else or something?
It is. So it is actually simulating the overall circuit. I mean we mathematically understood that that this circuit will give 00 plus 11 over root 2, isn't it? So it is clear to us now. I told you that our simulator gives the output as 0 0 with amplitude this one, 1 1 with this one. So how simulator is doing the simulation, that's what I am trying to tell you, that simulator is taking this circuit in this form. It's calculating the G1 first, then the G2, is well known, then it actually does the tensor product of this gate, and then it multiplies like this, like matrix multiplication, and gives us the output as 1 over root 2 0 and 1 over root 2 1 1. So this is the simulator is doing, which is abstract to us, but I am here to show you what actually simulator is doing with the circuit.
Okay, the background mathematics were actually calculated.
Okay, one more.
Yes.
Okay, one more thing. Samantha Tonai Chattopadhyay is asking
Yes.
why tensor product is not applied here.
Because this is fundamental actually. This is nothing like a rocket science that I can apply, because you have to understand that if you do tensor product here, so dimension will be high, and it will not give us our desired result. We need our desired result. So that's why we are doing the tensor product between the 2 qubit registers gates, and we are doing the matrix multiplication to get the actual outcome or the desired outcome.
Okay. He replied he understand.
Okay, thank you so much.
Okay. One more. Another thing is Dr. Lata asking why to do matrix multiplication in reverse order. Matrix multiplication is not commutative.
No, ma'am. Actually, if you don't do this in reverse order, you will not get the actual outcome. If you so you have the circuit in your hand, you have the matrices in your hand. If you do the left to right multiplication, you will not have the desired output. You can try this at your home. You will not have the desired output. If you do the reverse matrix multiplication, then only you will have the desired output.
I
You understand.
Thank you.
have one question.
Yeah.
Why you have taken this? Somebody has already asked the same question, but your answer is not very clear to me. Like, why you take the product? Product has got a different meaning. When you take a matrix product, we have got a different meaning. Now, the meaning is not very clear here. Why you multiply G2 by G1?
This G2 by G1?
Yeah, why you multiply this?
Okay.
What is the objective question?
Yes. So just you are asking me that why I am doing the matrix multiplication. So you have a C naught. So you have a C naught. So you have H tensor I. So it is clear that why we are doing the tensor product over H and I, and followed by one C naught gate, and why we are multiplying this C naught with H tensor I, because we need to understand what is happening between these matrices, isn't it? So if we multiply them, then only we'll have the by C naught, we only have when we are doing the matrix multiplication, nothing else. There is no rocket science. So if we do the matrix multiplication, then we can have the ultimate matrix product of this quantum gates.
So what does it mean? Suppose G1 is, say, my initial state, and then we want to convert it to something new, a new state.
No, sir. So actually, in timestamp 1, it is G1. So first of all, we have H and I, and second in second timestamp we have C naught gate. So from this portion, we have this matrix. So it's all about matrix. When we are simulating any quantum circuit, it's all about matrix. It's nothing like mathematically we are going to prove or we are going to have the desired output. It's all about matrix, because H is represented by 1 over, as I shown you, that 1 over root 2, 1 over root 2, 1 over root 2 minus 1 over root 2, and I is nothing but 1001. And G2 gate, that C naught gate, is nothing but 100001000010. Now we have this Z1, like Z1, this one as tensor product, which is nothing but this matrix, and this is nothing but G2. Now we have to somehow get the overall matrix of this total circuit. So that's why we are multiplying these two, that G1 and G2, to get the G. So this G is nothing but the overall circuit. So this defines a complete. So if I let me write it down. I am very much amazed that you all are questioning me, and I am very much happy to answer all the doubts here. So H is a matrix which is nothing but a unitary matrix, as all the respected speakers had already mentioned. I is also a unitary matrix. C naught is also a unitary matrix. Now H has some value as a matrix. I has some value, C naught has a value. So overall we need a matrix so that our simulator can give a result from understanding this, by understanding this individual gates. So if it give, so final G is giving me H tensor I multiplied by C naught gate. So that means C naught gate H tensor I. So G is giving me all the information of these three matrix by doing tensor product and the matrix multiplication. So now I can have the matrix, this matrix information, this overall matrix information in our hand. I think now it's much visible to everyone. So what actually G is?
Hello, is it like cascading of gates or something? I mean,
yes, it kind of. You can like, so this is the fundamental property of doing the simulation of quantum circuit. So I'm doing nothing rocket science here. This is the fundamental representation of the simulation of simulating the quantum circuit. So we do tensor between two quantum gates when they are having in two different quantum bits or quantum registers, and we do the multiplication when we have the overall timestamp G1, G2, like that. So now in G we have the overall complete information of the matrix. So let me just cross this. Yes. So as I already mentioned that we have to again multiply this thing with 0, 0, because we need the output. So we have the 1 over root 2 0, 0, 1 over root 2 1, 1 as our output, as all the simulator gives us as a result. So next thing I want to discuss is Grover's algorithm, because I'm going to demonstrate an computational problem based on Grover's algorithm. So Grover's algorithm has already been discussed by Sushmita ma'am and Maulana sir. I'm just taking 2 or 3 odd minutes So as we know that Grover's algorithm, I think simulation part is clear to all. Now we are going to demonstrate, going to take a look on a demonstration of a problem based on quantum algorithm, that is Grover's algorithm. So Grover's algorithm can identify an item from an unstructured list where if there are n elements, it can search with the big O of root over of n times or the big O root over of n iterations. So in Grover's algorithm, there are mainly three main parts. First one is initialization. So we have to encode your data, which for the given problem so you have to first encode your data for the given problem and followed by the Hadamard for the superposition, because to get the quantum advantage, we need to superpose all the data for the given problem. That is already been discussed. So here you can see that I have initialized some zeros, and I have do the Hadamard on this, and we'll have the superposed states of all possible combination of the data. So this is the oracle part. So this is the most interesting part, I must say, in Grover's algorithm, because you have to define your oracle by your own for the given problem. That means, what does it mean? Means when you have a problem or computational problem, you have to define your oracle for that specific problem in such a way that after applying this oracle U0 or the unitary function of oracle, your desired output gets flipped. So what does it mean? It means the amplitude, all the unmarked or the non-desired items will remain positive as amplitude, and the desired item will be flipped. So these actually are done by the oracle. Next part is diffusion. It is not problem specific. It is well defined. It is defined by the Professor Love Prover in 1996 in his famous algorithm. So we don't need to bother about the diffusion operator. It is completely ready-made. So if you do the diffusion, as you know that it will average all the elements of the given problem, and it will just by the wonderful property of interference in quantum mechanics, it will give all the amplitude to the desired item, and it will become more and the desired result is become more higher probability towards 1. So this is actually desired. So from this Grover's algorithm, the takeaway is we need to define the data first. We need to encode the data into quantum paradigm, and we need to apply the oracle function to flip the desired state. But we will not have the desired state at one shot, because it is still in similar in same probability or the amplitude. So if you measure the quantum state over here, you will have the same probability amplitude, same probability of all the items. So you don't get any advantage by doing it one shot. So you need to apply the diffusion, and you need to iterate it at least root over of n times. M is number of mark state. As we are considering here, there is one mark state. Then you need to repeat this root over n times. Then only you will have the desired output with higher probability, like 1. So this is all about Grover's algorithm. And so today I'm going to present implementation of graph coloring problem. using Grover's algorithm. So graph coloring is well known to all of you, I believe. It's a very trivial problem. Like you have a graph and you cannot color two adjacent vertices. So for this, first of all, you need to define the you need to encode the data of the graph. So you first of all you have the only adjacency of a matrix in your hand, because I have given a graph to you. So now you have adjacency matrix of that graph, and from that adjacency matrix we have two knowledge of it. One is the number of vertices we have in the graph, and another is edge of the graph. So from the knowledge of nodes and edges, we have to define our data, which we are going to encode into the Grover's algorithm. So as I mentioned that we can have a n number of nodes in a graph, and suppose there is a k number of color is given. From k number of color, you have to color the graph appropriately. Like two adjacent nodes will not have same color. So for this like suppose you have a two color, then it should be log 2, that means 1, and n is nothing but 6. Like n is nothing but, suppose you have five nodes graph, so it will become 5 into 1. That means your initial data qubit will be 5. What does it mean? That means we can define the vertices, that 5 vertices, as 5 number of qubits when the k is 2. What does it mean? Let me write over here, because this is very important. Like you have a graph like 5 number of nodes. Okay, then n is nothing but 5, and suppose k is given as 2. You need to color this graph with 2 different colors. Okay, so I'm telling you that you need at least m equals to n into log 2k. That means 5 into log of 2 into 2. That means 5 into 1. That means 5. Okay, so you need 5 different qubits to define this nodes as qubits. All right, so why is it so? Because this 2 to the power, this 5 qubits, if I have the Hadamard with this, we can have 2 to the power 5. That means 32 number of states in our hand. This is nothing but 32 possibilities or possible ways of coloring these 5 nodes. I think this is clear to all of you. Because we have 2 number of color, we can color this 5 node graph to 32 in 32 ways. Okay, so that's why we're taking this 5 qubits as data qubits. Okay, and what we are going to check, we going to check that this 5 node will have different colors if they are having edges in between them. So we need to check that that on those 5 nodes there are no adjacent if there are adjacent edges, then we cannot do the coloring with same color. So that's why I need to add n number of more ancilla qubits initialized with 1 to check this 5 nodes are having different colors if they are having edges between them. So it requires at most number of edges, ancilla qubits. It can be optimized further, and this is the final output qubit, as already shown by Shushmita ma'am and Amlan sir, that we need one output qubit to get the desired result. So after Hadamard transformation, we can have the all possible colored vertices in our hand, all possible colored vertices, and to do the oracle operation or the comparison operation that the two adjacent vertices are not having same color, we need this much of ancilla qubits, and final output qubit initialized with Hadamard for the flip operation, that oracle's flip operation. So what is actually happening later? So oracle, in our case, that coloring problem, for that coloring problem, we need to define some comparator as oracle. Okay, so we need to compare two nodes in such a way that it will give me 0 if they are having the same color like A and B, and it will give 1 if they are having the different color. All right, so this is the comparator circuit. You can easily check at your home that if it is 0 0, it will give 0. If it is different like 0 1 or 1 0, it will give 1 as output, and if it is 1 1, it will give again 0, because 1 1 is same color. So our oracle circuit is going to be built by this comparator circuit. So this is the overall view of oracular circuit. We are initializing the data qubits, which are nodes, along with the colors. These are the ancilla qubits or working qubits. We need to do the comparison comparison between the nodes, and this is the final output qubit. So we need, you can see, we need one MCT gate for this to amalgamate everything into this single output qubit to get the desired result. And diffusion operator I haven't discussed now, that's why it is dotted here. So next is diffusion operator. We don't have to bother about diffusion operator. It is already defined, and it is not problem specific. We need to define the oracle for the given problem. So this is the overall circuit view. This is the oracle part and the diffusion part. If you iterate this root over of n times, then you will have the desired output, as I mentioned in the last slide of my presentation. Okay. So up to now, is there any confusion or any question? Because I'm going to demonstrate a small problem within maybe 10 minutes. Is there any?
Yeah, I have one question.
Yeah.
In the Grover's algorithm,
Yes,
you say that to search a particular number, the time complexity will be of the order square root of n.
Yes.
Now, if, say for instance, the number is not there, then how do you apply the Grover's algorithm? Number not there, but still I want to search.
Yes.
And how do you obtain the probability?
Yes. So after root over of n times, it will fail. It will give equal probability. So we have to understand from the results that there is no desired result in that particular array or the qubit registers. So we have to run root over of n times, then only we'll have the desired result. If we don't have the desired result, that means that data is missing on that qubit register. Like what you do in the linear search, you have to search n number of so if you have n number of array, then you have to search all over the array, and if you find that desired result, then you can say that yes, I got the result. But if you if you gone through the all over the n items and you don't find the desired result, then you declare the item is not found. Similarly, you have to run this only root over of n times. If you get higher probability output, then you can say that yes, this is my desired result. Otherwise, you can say that the desired result is not present here.
Okay. Understood. And the last question is,
Yes,
your simulator, what the simulator you have mentioned here,
Yeah.
is it a normal, is it our classical computer or it is really a quantum computer?
No, this is classical. Like Qiskit, you can.
Usually, we are using a simulator. So simulator, I can also do it in my machine. So we are not we are not doing anything with the quantum computer.
No, sir. No, sir. We are not doing anything with it.
Thank you very much.
So what actually we are doing, we are actually applying the advantage of HPC, and we are just increasing our qubits facility, because IBM's Qiskit is giving you 32 qubits operation. So we are offering you 41 qubits machine. So you can have the more complex problem with the simulation results. All right. So I believe there is no confusion or no issue. So can I take 10 minutes to demonstrate, because I
Yes.
I am
Yes, you
already
can
running
continue.
late. I am already running late, but
It's okay. You can continue.
Yeah, because I believe it's much more required to understand everything. Otherwise,
Yes. Thank you. Continue.
just a minute. Okay. Is it visible to everyone?
Yes, it is visible.
Yeah. So so I have taken a very simple example that I have done during my earlier days when I was learning quantum computing back in 2014-15 during my master thesis. So so demonstrate before you, because I believe if I take harder problems, it will be very difficult, and time is very much constant here. So as you can see that, suppose in an examination, two students can sit in a row like this, and let there be two sets of questions having different colors to make them distinguishable. So like we have like blue color question and red color question. So two consecutive students cannot have the same colored question. It is very much acceptable. Suppose there are 6 students, like 1, 2, 3, 4, 6, in the examination hall, sitting in 3 consecutive benches like this. This scenario can be mapped into a graph where nodes represent students. You can see that 1, 2, 3, 4, 5, 6, and the edges represent the adjacency between them. That means 1 and 3 will not have the same color question, and 1 and 2 will not have the same color question, but 1 and 4, as they are diagonally sitting, they can have the same color question. So that is, I have written here, like we must make sure that no two adjacent students can have same color of question set. Thus this problem becomes graph coloring problem as shown below. I believe everyone has understood this becomes a graph coloring problem where I cannot give same color questions between 1 and 2 or 1 and 3, but I can give same color question to 1 and 4 or 1 and 5 or 4 and 5. Okay. So we are going to solve this examination. What should I say? I have to give a name. Examination sitting problem. Yeah, sitting problem as a graph coloring problem, and we are going to solve this problem with the Grover's algorithm. And we can see that, and we have already defined how we can encode data from the adjacency matrix or the graph informations. That we have the 6 number of nodes, and there are 7 number of edges, and we have to color this thing with two colors. All right, so that means our so that means our as you know that our data qubit will become m equals to n is 6 into log 2 2, that means 1. That means our data qubits become 6. Our ancilla qubits will become 7 because there are 7 edges and we need to compare at most 7 times. So that's why we need 7 ancilla qubits to store the intermediate outcome of that comparison results, and finally one output qubit. That means we have total 6 plus 7 plus 1, which is 14 number of qubits in our hand. So as we know that we have to first of all import all the necessary gates, and this I have import to visualize the output results uh, more more good way, I must say. And I have defined the program here, and here I have taken the qubits as 14 because we need 14 qubits, like I have mentioned here. First 6 represent 6 colored vertices, which will have these 2 to the power 6 number of possibilities of colored vertices, and next 7 ancilla to check that those 6 qubits, those 6 nodes are having different colors or not, if they are having the edges in between them, and final qubit for the output. So so as we uh, earlier seen in my slides, that we have to allocate this qubits as I have allocate this as q qubits. Now I have to so let me run this. Okay, now I have to initialize my first 6 data qubits with Hadamard. As you can see, 0 to 5 I have applied Hadamard gate to get all possible information of colored vertices. That means now we have 2 to the power 6, that means 64 possibilities of colored vertices. That means we can color with 2 colors that 6 node graphs in 64 ways. So we have all the 64 possible colored vertices in our hand right now. And as we mentioned that ancilla qubits needs to be initialized with 1 to implement the comparator circuit that I have shown. So I am applying the X gate on the ancilla qubits for becoming the ancilla qubits to 1, because it default initialized with 0. And finally I have applied the Hadamard on the output qubit. So this is my comparator circuit that I have shown in the slides, and I have to compare the node 1 and node 2, which is nothing but the qubit 1 and qubit 2, as we are defining the nodes as qubit, like qubit node 0 is node 1 is qubit 1, node 2 is qubit 2, like this. So we have to compare between this 1 and 2, because there is an edge. So we are implying a comparator circuit between qubit 1 and qubit 2, or you can say node 1 and node 2. So you can see that this is the comparator circuit. So I just move forward this one for the sake of time, because we need to apply this comparator between 1 and 2, 1 and 3, 2 and 4, then 3 and 4, 3 and 5, 5 and 6, 4 and 6. So you can see that I have implied comparator between 1 and 2, 1 and 3, 2 and 4, 3 and 4, 3 and 5, 4 and 6, and 5 and 6 finally. And I have mentioned that to get all the information of this comparator results, we need to apply MCT gate to flip the oracle in the output qubit. So we have applied the MCT gate. So we have to define the MCT gate in our QLM like this, and you have as you know that you need to do the mirror circuit as well to get the actual desired result. So we do the so we again apply the all the comparator circuit here. So let me run all of this, then only we'll have the result. Just give me 30 seconds to run all this. Yes. So I'm just amalgamating everything, and I'm just converting that quantum program into circuit, and we'll have the portrait of the circuit over here. So yes, so this is the overall circuit we have. We have, like you can see that we have 14 number of qubits, and first 6 are initialized with Hadamard, and then the NOT gate, because we need one over here, and we have applied the comparator circuit between first node and the second node. Is these nodes are having same color or not to check, and we are storing this output in the first ancilla qubit. Like this, we have checked for 1 and 3 first and third node to check and store the result in the second ancilla qubit. Like this, we have done this for 7 edges we have. So we have stored in the 7 ancilla qubits, and finally we have applied the MCT gate to store the final outcome of this 7 ancilla qubits into the last qubit, from which we can flip the desired output. And after that, we need this mirror circuit that I have already discussed, that we need mirror circuit to get the desired result. All right, so this is the overall view of our simple problem, but it's not so simple circuit, whatever. And this is the and now we have to define the linear simulator, and we have created the job for this particular circuit, and we have submit the job in the linear QPU, and this is the final. So let me run this. This is the final results we have. So this is very much difficult. All are like positive. You have to search. Yes, this one and this one is negative, because these are the desired results we are having right now. So if I suppose what is happening? Okay. So okay, no, don't bother this one. So we can see from the pictorial view. So if we run this thing, yes, so you can see that these are the undesired or non-desired outcomes, or the unmarked states, which are not having the appropriate colors on the nodes, and these are the desired results we are having. So these are becomes negative amplitudes, and these are the positive amplitudes. Now, but if we measure them, the probability will remain same as the amplitude is remain same, and it is nothing but the square of the amplitude. So the amplitude will remain same, and it will not give any desired result in one shot. Now we have to apply the diffusion operator. So diffusion is not problem specific; it is already defined. So this is the diffusion circuit, and if you run this thing, yes, you can see that first of all we have applied the so this is the initialization part. Next is oracle part having the comparator circuits, and finally we have the diffusion operator at the last of the circuit. So if we finally we want to see the output of the circuit. So what is it? So now you can see that it becomes all the amplitude becomes negative now, because we have do the average of the inversion, so which is nothing but amplitude amplification, and interference has happened already, so that non-desired results are actually giving their amplitude to the desired result to become higher probabilistic result for the desired outputs. So if we see the final pictorial view, so now you can see that these are the only desired colored nodes that we can have, and only one iteration, after only one iteration, it is showing that it is lots it is much higher than the non-desired outcomes. And if you iterate this thing for more 2-3 times, it will become almost 50.50 and 0.50, and it will become 0. So final result, what is the final result? So this is nothing but the colored nodes, we have one, like if we take red as 0 or and blue as 1, so it is nothing but 0 1 1 0 0 1. So this is nothing but 0 1 1 0 0 1, and another output can be written as 1 0 0 1 1 0. So this is nothing but 1 0 0. And apart from these two outcomes, there are 62 more outcomes, but they cannot solve this examination seating problem, because this can be so if you give this person blue question paper and this person blue question paper, then it will not make any sense. So finally we have solved a coloring problem, which is itself a NP problem, but as we have solved the two coloring problem, it's a polynomial time solvable problem. So it is very easy to simulate here in classical computer. So so you can see the final desired result in your hand. So this is the demonstration I have today for you. So if you have any question regarding this demonstration, you can ask me right now. So all over from my side. Hello.
Yes. Participants, if have any questions, they can ask.
I have one very simple
question.
Yeah, one question, but that is very trivial. The question is, the Grover's algorithm is very interesting. I found it's very interesting. To search a number within, say, square root of n time complexity. Now, can you give us some idea how we can get maybe the largest number or the smallest number in quantum computer? Any idea? Suppose I want to get the largest or the smallest. Any algorithm you know? Quantum algorithm?
Quantum algorithm to get the largest from no. First of all, we have to understand that we are not going to solve all the problems in the world with quantum computer. It's not possible. We are targeting the most complex computational problems, which are like NP problems we know, and I believe that to find a largest number or the smallest number, our classical computer is good enough to find find the largest number or the smallest number. But if you want to demonstrate through Grover's algorithm, yes, it's possible. You can easily define your oracle in such a way that the black box will find the largest number among all the numbers in the list, and you'll give the higher probability for the desired result. Definitely, Grover's algorithm will solve the problem.
Okay, okay, okay.
And one more point I want to add here. Suppose you have a array like a 2 to the power n number of lists. Then only this quantum computer or the quantum algorithms will get into the actions, because 2 to the power n or the exponential problems will take much time to solve in the classical computer or the parallel computer. For parallel computer, you need more resources. So quantum computer is going to solve the more complex problems.
And the last question is, suppose I develop a simulator to do this type of experiment. Now, will it be enough for to submission of a PhD thesis for a student?
So I'm not in a position right now because I'm still pursuing my PhD. But
Yeah,
I
know,
believe
yes,
but I believe now we are in 2021, and back in 2015-16, when I was starting or planning my PhD, that time it was a good problem, I believe, because in earlier days I made not only me, I and my 2 or 3 friends made a quantum simulator, small quantum simulator. So but I believe this is you have to think much more to complete PhD in quantum domain right now, because there are many exploration in last 2-3 years.
Yes. Actually, just interrupting you. Actually, so sir, if your student have implement any simulator or discover any simulator, this can be his or her PhD thesis paper. There will be no problem. Okay, you can publish such things, how your simulator is works, those things in any journal paper, and this can be well enough to get a PhD degree.
Yeah, yes, actually, yes.
I think
so
you got my point, sir.
Yes. I just want to add one more thing here, because I have just shown you the linear property, the linear algebra simulation here. So there are multiple simulation simulator like MPS, matrix product state, which is very much popular nowadays because we have the NIST quantum computer. So MPS is very much popular. BDD based, which so using BDD you can simulate 100 number of qubits in your classical computer. So if you want to propose a new quantum simulator, you have to work on the state of the art work first. Then you can tell the journals or the conferences that yes, we have the better simulator in our hand as compared to the state of the art simulators. Then only you have the good results.
Thank you very much, because we are getting a lot of good students in our college. So I'm thinking that I should employ some student and do it very fast.
That's great.
Thank you very much.
Okay, thank you. Is there any questions left? Okay, if participants, you have any questions, you can mail to our speaker, Mr. Amit Saha. Okay, so sir, if you kindly share your email ID with the participant.
I think there are some questions I have.
One question, actually, the Dr. Lata is asking about the limitation and disadvantage of your simulator.
Okay. I can see 3 questions. Okay. First question is, what are the disadvantages and limitations of such simulators? Okay, ma'am. Like it's actually running on the classical hardware, and classical hardware has some limitations, as you can see that we reach to the Moore's law, isn't it? So after all this thing, we are actually simulating the quantum circuits on the classical platform. That means we will have maximum 50 or 50 odd qubits quantum simulator in our hand in very near future. Not much that if we have the 100 qubit machine simulator, if we have the 100 qubit simulator, then we'll need very large number of supercomputer work in a distributed manner. So it's not very cost effective, not very trivial as well. And only combinatorial problem can be solved. No. This is not true, because combinatorial optimization problem are being addressed nowadays by the computer scientists, because using variational quantum eigensolver or the QAOA algorithm, we can solve those particular combinatorial optimization problem. That's why we are targeting right now those combinatorial optimization problem. Any problem can be addressed by the quantum computer in future, when we'll have the scalable fault tolerant quantum computer in our hand, maybe down the line 10 to 15 years. Okay, and how is TensorFlow quantum to implement works? I think TensorFlow is more about machine learning, I believe, and yes, there are some works with quantum machine learning. Some groups are working as like they are taking the classical problems of machine learning and doing the superposition of it and giving the quadratic speed up using the quantum algorithms, and some are doing with the QAOA or the VQE algorithm, which is I believe more technical indeed right now. And quantum TensorFlow is providing some libraries to work on quantum machine learnings, and it's a good platform. Yeah. Anything else? Okay.
Hello. So can I ask one question? A very short question, actually.
Yes, yes, you can.
Actually, sir, you told that any problem in future can be addressed by this quantum computer, and now we know that there are NP-complete problem, NP-hard problem kind of things, and those NP-hard problems can be addressed by quantum computer, or will there be any kind of things which will be called NP-hard or polynomially unsolvable problems?
Well, just if Dr. Jadhav sir, can I have 5 minutes? I'll show one slide if everyone agrees, because already we are running late. I have.
Yes, you can proceed.
Yeah, thank you.
Yes.
This is a very important question, and I just want to give a proper view of your answer. I just can't skip by giving you a simple answer. So let me just a minute. Yes. Is it visible?
Yes, yes, visible.
Okay, okay.
That's
Yes,
visible.
Yes, that's good. So
Yes, it is visible.
yeah, so I just keep all the basic slides from today's talk, but I always try to mention these things in other talks. So this is the complete view of a complexity classes. So we know that this is a polynomial class problems, and this can be efficiently solved by the classical computers, that we know, and rest of these are NP, and this is the hardest problem of NP complete, and apart from this there are some NP hard problems that we know. So what actually quantum computers are targeting, what are the problems especially? So this is the NP problems actually quantum computers are targeting. This is the NP problems, because this has been proved that NP complete problems will give only quadratic speed up by using quantum computers. So that's why so for a industry perspective, the quadratic speed up is like $1 billion of income. So whenever we have the fault tolerant scalable quantum computer, this NP complete problem will be addressed by the quantum computers, because this requires large number of qubits. So by solving this NP complete problems, industry will earn billion of dollars. But now these are the complexity classes problems, like Shushmita ma'am has already discussed the Shor's algorithm, the famous algorithm. So that factorization problem, that factorize a large number into two prime numbers, so that problem comes in this NP classes, and this problem can be addressed by the quantum computers, which we have addressed as BQP, bounded error quantum problem classes. So bounded error, that means there might be some errors, but these exponential problems, like Shor did, that exponential problem can be solved in polynomial time, which is n to the power cube. So this is the complexity class we are targeting, and we are just giving the exponential speed up of these problems, and it is already proved that NP complete problems will give quadratic speed up as it does for Grover's algorithm or quantum walk or QAOA or VQE problems or the quantum machine learning problems. I think it's pretty much clear now.
Thank you, sir. It's little bit, but it's not a very easy thing to understand in this small time. I know that.
Yeah, if you have any doubt, you can reach me.
Sure. Actually, what I mean to say that what are the main constant is the time complexity, and if the quantum computer is going to address this time complexity, I mean speed up the system, then how it is going to make advantage for us for solving these hard problems. That was actually my doubt. Actually.
So you are asking me to show the real life problems more. I mean, what are the problems we are going to address?
If the organizers allow, then I will obviously be very grateful to you if you.
Okay. Okay, so we are here to learn. So I don't think time will be much constraint here.
Okay.
So these are the applications domain. Right now we have targeted, as I am right now in the industry. So these are the main 7 industry sectors, like manufacturing, public sector and defense, financial service, telecom, resource, healthcare, life sciences. So these are the main sectors we are targeting. And I have in my slides, like chemistry, we can use VQE problem to solve the difficult chemistry problem, by which we can discover and discover the various chemical structures In pharmaceutical, we can have the drugs. We can have the like we all know that for COVID-19 that we need some protein structure, that mRNA structure. So if we have the powerful quantum computer, we can uh, we can simulate that overall protein structure in much less time compared to today's supercomputer. So in cryptography, BAM already told that Shor's algorithm. In finance sector, we can use quantum random walk. So I'm right now working on quantum walk. So you can optimize various algorithm in finance sector. You can you can predict the stock. Then you can be rich one day by predicting these stocks if you have the most powerful quantum computer in your hand. Oil prospection, it's a famous problem that is solving that is being addressed by IBM. They are actually searching this search space of in the art from where we can have the best quality and the huge number of oil we can get. Combinatorial optimization problem that Lota ma'am has already mentioned, and we know that computer science problems is all about combinatorial optimization problem. Amazon is earning so much money nowadays and by solving this combinatorial optimization problem, like the traveling salesman problem. How they can first take the order and supply to the actual receiver. So this a very good problem in computer science, and we are using like QAOA that ma'am has already discussed yesterday. And machine learning, I think today we had a session on machine learning. So in QML also we are actually applying quantum computer. So yeah, I think now it's pretty much clear what are the sectors we are targeting. Yeah, thank you, sir.
Thank you very much.
Okay, thank you.
Sorry, Jadov sir.
No, don't be. We are here to learn. Okay, we have organized this STTP to share the knowledge with the participants. If they get benefited, then it will be good for us. Our main aim is to share the knowledge with the participants, and we are thankful to the participants. They are interacting with the speakers, and they are too much. That means, in that sense, they are too much interested and excited, and they are asking the questions to the speaker about their doubts. So
yes, absolutely. I am very much thankful to Professor Shah for his interactive sessions.
Thank you so much.
Thank you very much, sir, for indulging us and all the questions. Thank you.
Okay. Thank you.
So Jadov sir, one last question and one last answer for 10 seconds. Can these machine learning problems be run in IBM Q? Yes, this can be run on IBM Q machine. So you have to just define the appropriate modules and the functions. You have to learn those functions for the IBM machine. You can run whatever you want to run in the IBM Q machine. Thank you.
Okay, thank you, Mr. Amit Saha. So giving your time and your lot of effort for us. Hope in future we will have your time again. Yes. So thank you. I am requesting Prem kindly display the appreciation.
Thank you.
So this is a little token of appreciation from our end, and thank you.
Just it is wrong.
It is not. It is wrong. Prem kindly.
No,
kindly
Prem.
check it.
That
Prem
one
is
is
not there.
Kunal.
Sorry to you.
Yes.
Oh, this is the right thing. Okay. Sorry for any inconvenience occurring to you. So that is from our side a little token of appreciation. So thank you for giving your time again. So thank you to all, and hope we'll have your time.
So
in our
you
future.
Yes. So one more question you asked. Okay. I have to write it in the chat box, isn't it? My email ID.
Okay, you just write down your email ID in the
Yes.
chat box. Participants, those who have still some questions, some query, they can directly communicate with Amit sir. He has already posted his email ID in the chat box. Kindly find the email ID from the chat box. Okay.
Okay. Thank you so much for inviting me, and good night all.
Okay, it's our pleasure to have you with us.
Thank you.
Okay, thank you and good night to all.
Thank you.
And we'll again meet in our next session